Hi, this is Module 21 of Two-Dimensional Dynamics. Today we're going to continue on, and instead of having a wheel rolling on a fixed straight line, we're going to have a wheel rolling on a fixed plane curve, or a curved surface. So here's a picture of the situation. We've got our wheel rolling to the right with an angular velocity of theta dot. The radius of the wheel is again little r. And so we're going to actually use normal and tangential components or coordinates for this particular system. And the reason I do that is because the wheel is rolling along a curved path, and so it'll be more convenient to use those coordinates. You'll recall our relative velocity equation, and again I'm going to go from the point of known velocity, which is the point of contact here, the instantaneous point of zero velocities, or center of zero velocity, and we're going to move to our unknown, which is the velocity of the center of the wheel. And so let's go ahead and write that equation, and I've got v of c is equal to v of the known, which is v of I, plus theta dot k, and that's crossed with, now we're going from our known to our unknown, and so we've got v of c is equal to 0 for the velocity of the instantaneous center, plus theta dot k. And again, we're using normal and tangential components. So going from I to c, we're going a distance of little r in the e normal direction. So this is little r in the e normal direction. And so I've got v of c equal to, magnitude is going to be r theta dot. Let's find the direction now. Using the right-hand rule, from my ij coordinate system, again, I've got k pointed into the board. I'm now going to cross k with e normal. So k is down into the board. I'm crossing it with I by the e sub n by the right-hand rule. That means that the direction now is e tangential. And so this is going to be e tangential. And that makes sense. The velocity is tangent to the path, and its magnitude, which we call the speed, is equal to r theta dot. Okay, let's continue on. So here is the velocity of the center of the wheel now. We want to find the acceleration of the center of the wheel. How do I do that? Okay, as before, we're going to go ahead and take the derivative, time derivative, and so we get the acceleration of c is equal to, r is a constant, but theta dot will change, or can change, so that's theta double dot, e tangential. Now this time, e tangential will also change direction as the wheel rolls along, and so it changes with respect to time, so I've got to use the product rule, and I've got plus r theta dot times the derivative of e tangential. And you'll need to recall from an earlier lesson at the beginning of the course that we developed the relationship that the derivative of e tangential is equal to s dot over rho e normal. And so let's go ahead and substitute that in. So we have a of c equals r theta double dot e tangential plus r theta dot s dot over rho e normal. S dot, however, as we said earlier, is the magnitude of the velocity, or equal to r theta dot. And so I can substitute that in, and I get a sub c, the acceleration of the center of the wheel, is equal to r theta double dot e tangential, plus, now since s dot is r theta dot, we have an r theta dot, that's going to be r theta dot squared over the radius of curvature to the center of the wheel, e normal. So now we have the acceleration of the center of the wheel, which includes both a tangential component and a radial or normal component directed radially inward. Okay, so far we know that the velocity of the instantaneous center is 0. We know that the velocity, we've found what the velocity of the center of the wheel is. We also found the acceleration of the center of the wheel. And so we now want to move on and find the last unknown point, which is the acceleration of the point of contact, or point I. And to do that, we're going to use our relative velocity equations going from our known, which is now the acceleration of the center of the wheel, to our unknown, which is the acceleration of the point of contact. So let's go ahead and write that equation, and I've got the acceleration of I is equal to the acceleration of c plus theta double dot k, crossed with r now from the known to the unknown. We know the acceleration at c, we don't know it at I, so this is going to be r from c to I, minus theta dot squared, r from c to I. R from c to I is going to be little r for the radius in the negative e normal direction. This is minus r in the e normal direction. And so I've got a sub I, oh, let's put it in over here too, minus r e sub normal. And so I've got a at the point I is equal to, let's go ahead and substitute in a at the center of the wheel. So that's going to be r theta double dot e sub tangential plus the quantity r theta dot squared over rho e normal. And then I've got k, which is into the board again, crossed with e normal. So by my right-hand rule, it's in the e tangential direction. Its magnitude is going to be r theta double dot. And so we've got minus r times theta double dot. So this is going to be minus r theta double dot. And we said k cross e normal is e tangential. And then I've got plus, because I got a negative times a negative, r theta dot squared e normal. Okay, now I see that actually this term and this term cancel. And so what I'm left with is the acceleration of the point of contact for a wheel rolling on a fixed plane curve is equal to, if I simplify that, I get 1 plus r over rho times r theta dot squared e normal. And that's where we'll leave off. And we'll come back next time and work a problem with a wheel.